Thank you very much. I'm deeply honored by this distinguished lecture, and I'm very grateful to the committee for inviting me and whoever has nominated me for this lecture. I'm also really happy to be here because it gives me the opportunity to talk about a topic that I really feel passionate about, and it's also a topic which is essentially pushing the frontier of ORMS, and I hope that I will be able to convey some of that to you. So this is the outline of the talk. I'm going to talk about some motivation first about this area. Then I'll talk about the role of ORMS in this field. Then I'll talk about 3 case studies, and then I conclude by talking about the perspective and the opportunities for ORMS in this area. So the number of disasters, natural disasters that are happening these days is basically growing exponentially. So you see this nice exponential curve at this point. It was a little bit of a dip in 2010, but 2011 came back with a big vengeance. This is also the cost of this disaster these days, about $350 billion at this point in 2011. So these are massive numbers. It's very difficult to comprehend really what they are. So what I'm going to do in the next couple of minutes to start the talk is giving you an idea of some of these disasters, and then I'll talk about them and how to actually address them in the rest of the talk. So the first one is Hurricane Irene. So this is a Category 3 hurricane that hit the United States in August 2011. It basically killed 56 people. It's about 15 billion in damage that are estimated at this point. So one of the things that this hurricane did was creating major outages on the east coast of the United States. So every one of the bubbles that you see there is a blackout. And at the time I was living in one of these bubbles probably here, and so it basically was 5 or 6 days without power. So that means no electricity, obviously, no refrigeration, no air conditioning, no computers, no phones after sometimes, and obviously no Facebook, no Twitter, and so on. Very dire situation to be in. And so these blackouts are a real issue. So this is obviously like, Hurricane Sandy, similar kinds of things. So this is hour after hours for this disaster. The kind of recovery that you needed to do for the power system and the transportation system. So to give you an idea of the cost of these blackouts, so the 24 hours blackout for San Diego 2 years ago cost about $100 million, cost about $100 million, and that's just 24 hours, okay? And that was basically tripping over line between Arizona and California. So that gives you the sense of the cost of any kind of blackout. Let me talk a little bit about the Japanese tsunami. You'll see they are very interesting issue for that particular disaster. There is a beautiful paper by some people at RPI and also their colleagues in Japan and in Australia. And they analyzed essentially that disaster. And it was a huge disaster in the sense that it was very widespread, but also very deep in some areas. And the tsunami was obviously very big, and the nuclear threat made the duration of this disaster very long. The response was catastrophic. It basically took about 6 days to actually provide any kind of release. And there were many issues subsequently. And one of the things that happened is that the logistics system completely failed. Some of the regional DC distribution centers, the city distribution center were damaged and completely unusable. And so there was no plan in Japan for a disaster that was that big. There were smaller plans for some regions, but not for something that big. And so what happened actually, which is pretty interesting, 2 things pretty interesting, is that the private logistic company actually saved the day. And also the international relief effort actually makes things worse. They actually overloaded every one of the DC that were still operational and slowed down the effort. And so I'll come back to that later on in the talk, so it's a very interesting point. I live in Australia right now, and so one of the most traumatic events in Australian life has been what is called now Black Saturday. It was a massive bushfires, and I have been in one of these last year, and this is pretty scary. These kinds of fires are really scary. And that particular disaster was essentially all over the state of Victoria. For those of you who don't know the area, Melbourne is located here, and this is the state of Victoria. And most of this was covered with fires, bushfires everywhere. And so essentially this was due to a major drought at that point. The temperature was very high, about 40 degrees Celsius, which is about 105 in Fahrenheit. Very strong winds. There are always strong winds in Victoria, but this is 120 kilometers, about 80 miles. And so some of the power lines fell and started on these fires. The response was truly, catastrophic. 60 people died, and the damage is over, 5 billion. Now, these disasters are not going to be disappearing, so this is essentially a very nice article from BlogNet saying that in the next, so one of the major global uncertainty risks in the Asia-Pacific region are natural disasters. It's one of the two big risk factors. And basically, 85% of the population affected by disaster live in those areas. And this exposure is going to double in the next 30 years because of rapid urbanization and also climate change, obviously. So I hope that I'm basically depressing you terribly at this point, but that article was actually pretty positive because it said we can do something about it. We can start mitigating these disasters, we can start doing something for actually responding better, and government should invest in those initiatives. And so that's essentially what I'm going to talk about. I'm going to talk about the role of ORMS to actually mitigate and respond and recover from these disasters. And I'm going to start with Katrina, which was a very traumatic event in the United States, but it was also a turning point in how the United States actually responded to this disaster. So before Katrina, essentially, the Department of Homeland Security and FEMA were mostly focusing on situational awareness, what's going to happen. And in Katrina, they knew pretty much what was going to happen. So they have a lot of situational awareness. But still, they didn't make the right decision. And essentially, this big report was, was written afterwards to analyze what went wrong. And this is a very interesting report. And one of the things that they are basically mentioning is that we need much better decision support for the people making these decisions under these very stressful, circumstances. And so we need to better mitigate the effect, we need to better use the resources and so on. So there are quotes in that report like the federal government must develop the capacity of developing large-scale logistic operations. So we started working essentially on disaster management at that point. And some of the things that I'm going to show you today are systems that we deployed since then. So let me give you a sense of the kinds of things that we can do. So we always start with an infrastructure. Basically, your power network, your transportation network, your gas network, people, obviously. And then you typically have some information of what the disaster is going to do. If it's a hurricane, you have the path of the hurricane. If it's a flood, you have the extent of the flood and the severity of the flood. And so you get these tracks, and for every one of these tracks of what the disaster can do, you can run fragility simulation, and we're going to tell you what kind of damages can happen inside that particular disaster. So let me show you, for instance, these are the tracks of Hurricane Irene that I mentioned before. And as you can see, these tracks are pretty accurate. They are not completely precise, but at the same time, they give you a very good understanding of what this hurricane is going to do. So you can reason about that. So essentially, to summarize, what we are basically doing is you start with an infrastructure. You have basically the track of the hurricanes in this particular case. You run the fragility scenario, the fragility simulation, and you get a large number of scenarios that you can start reasoning with. Okay? And the kind of decisions that we're going to do are basically what we typically do in optimization. We have to make decisions at different levels. At the strategic level, we have to start mitigation measures. We have to start allocating resources, stockpiling, and things like this. And then you move at the tactical level where essentially you see the hurricane coming and you can start repositioning your resources. For instance, in Sandy, I was on 95, 2 or 3 days after the disaster, and you could see trucks coming from New England going to New York City and things like this. Then you have the response, which is all about evacuation, search and rescue, relief distributions and things like that. And last but not least, because this is also a very important step, you have recovery. How fast can you recover the infrastructure after the disaster? So these are all the kinds of decisions that we have to make, okay? And so there are some beautiful articles actually reviewing the complexity of this problem. So this is a nice paper by the team in Georgia Tech. And essentially what these papers are doing is looking really at what are the features of these problems. And when you look at them, they make the computational complexity of these problems really, really difficult. Why? Because typically you are combining many optimization problems, let's say routing, inventory, and location at the same time. Obviously, you need to have a fast response time. You don't have 6 months to react to these disasters, and in most cases, essentially, it's a stochastic environment, right? So you don't really know what the disaster is going to do. Another very interesting thing, and I will come back to that later on, is that the objective functions that we are optimizing are very different from what we typically do in optimization. We are not maximizing profit or minimizing cost. So you have these kinds of, social welfare objective, and they completely change the nature of the optimization problems. think of it, it can be a make-style objective for a routing problem. So kind of a scaling objective, but this time for a routing problem. And I'll come back to that. They make these problems very difficult. So it's well recognized that these computational difficulties are major, and even for very small instances, off-the-shelf packages cannot even solve these problems reasonably well. And I would actually go further than just humanitarian logistics. So this is computational disaster management is about optimizing over very complex infrastructure, like the power system, the gas network, and things like that. And in addition to that, you can say that we are optimizing against nature. Okay, we are optimizing against complex physical phenomena, and also we have to take into account how people react in those environments, because they mostly don't do what you want them to do. And finally, I think disaster management is a line-going process. You have always to constantly monitor and update your system. And once again, I will talk about some of these issues at the end of the talk. But it's a very complex problem. So what I'm going to do now is move to some of the case studies so that I can illustrate this on a very specific example. And for that, I have to put some disclaimer here. These are very difficult problems. You have to be very humble. There is no way, given the state of the technology right now, to find optimal solution for these problems. So typically what we do is we have a very pragmatic methodology. We look at the problems and we look at the practice in the field, and we try to do better. We try to improve what is going on. And in general, we try to give bounds such that we can measure how far we would be from an optimal solution. When we can do that, it's not always easy to do that. Then we identify bottlenecks and we iterate. Okay, so that's typically what we do. In some of the examples that I'm going to show you, we are basically looking at the first attempts to solve some of these problems. So I expect that people, in the next couple of years, will provide significant improvement to what we have done. And finally, I want to say that I will focus on the high-level ideas. I will go into some technical details, but there are many aspects that I want to cover. But we have papers on all of these. Some of the systems that I got, these case studies are actually deployed, so they were used for Hurricane Irene and Hurricane Sandy through our collaboration with Los Alamos National Laboratory. So I'm going to start with evacuation, and I'm going to tell you why in a moment. The first reason is that, when I came to Australia, people were, very worried about bushfires, and then they told me about this, fire policy, which is stay in your home and defend it, or, be buried. And I was really shocked. And even after the Black Saturday, the commissioner who was responsible for the response, and as I told you, it was a really bad response, said that there used to be policy where you can tell people what to do, but I don't believe in that. People are adults; they should make their own decision. And this was very funny because my friends at Los Alamos had told me this story about the bushfires in Los Alamos, and this is a city of scientists, right? So all crazy scientists. And essentially, there's this evacuation plan for these bushfires, and they knew what to do. And then when the bushfires happened, none of them actually, some of them, most of them actually didn't follow the plan. The first thing they did was going essentially to pick up the kids, but the kids were saved, right? The buses were at the schools and so on. And if you know how Los Alamos is organized, there are plenty of canyons that generating massive, traffic jams, and therefore very few, the evacuation was terrible. So I wanted to work on this, and I'm going to show you an example for the Sydney region. So this is one of the most beautiful cities in the world. And next to Sydney, there is this massive floodplain there. This is West Sydney. These are the Blue Mountains, and that's basically a catchment area. That's where the precipitations are accumulating. And in between the two, there is this dam here, which is the Warragamba Dam. That's what you see over there. And every year it spills over. There are floods and so on. And people are really worried about this. The town councils in that region want the government to actually take preventive measures and build responses for this area. If they have a major flood, it's going to be about $8 billion in cost. So essentially, we started working on such a scenario, and essentially we looked at evacuating about 75,000 people. Typically, the profile that people in the state emergency services there are looking at is basically 50 residential zone, about 10 evacuation centers where you can put people, and they basically are looking at about 500 road segments and about 125 transit nodes. The flooding scenarios that we are looking at is like one of the major floods in history. And we look at the population increase in West Sydney from what it is now, and increase it from 10 to 300%, because these cities in Australia are growing pretty fast. So what we did is essentially building this integrated flood management system. We start with a geographic information system, which takes essentially every information that we need, the residential zone, the road network, the elevation data. We have essentially the terrain, 5 by 5 square meters resolution. And the first thing we did was developing these flood simulation tools to the hydraulic dynamic model for essentially modeling what the flood is about. And then once we have that, we could start planning escaping evacuation, and so maximizing the number of people we can evacuate. We are also doing mitigation measure at this point. So let me talk a little bit about the 2D hydraulic model, the hydrodynamic model. So this is essentially the traditional Navier-Stokes equations, but for shallow water. You essentially have equations for mass conservation and then momentum in X and Y. And the interesting thing about this is, there is a very interesting relationship with video games. I never thought that, my son is actually playing this like crazy. And so I never thought that this was useful for anything, but actually it's very useful for flood simulation. Why? Because essentially graphic processors these days are dealing with millions and millions of very little triangles. And what is a flood simulation? It's essentially dealing with many millions of points inside a grid. So the technology that has been developed essentially for entertaining my son is very useful for flood simulation, and we can get close to real-time flood simulation these days. So this is a flood simulation for the Hawkesbury-Napier region. The dam is over there, so this is what we built. Okay, the dam is over here, and you see the flood extent. So what you get when you do a simulation like that is obviously the flood extent. For every one of the 5 by 5 square meters, you get the elevation of the data. You also get the speed, in X and Y, and that basically tells you what you have to evacuate, which roads are going to be blocked, and things like this. Okay, so this is essentially the flood simulation that we have. It's very precise. It basically, reproduces really what happened in practice in the large flood that I mentioned. So once you have that, you can start reasoning about your network. So, as I told you, we basically take this, region and we cluster it in a big network where you have the various evacuation, residential zone that you have to evacuate, the evacuation centers that you see over there, and all the road segments. And obviously one of the things that we have to do is to make sure that we have the information, when do we have to evacuate a particular node, okay? So we know the time at which that residential area is going to be flooded, and we know how many people are staying there, living there. So we also know for every one of the roads when it's going to be flooded, how fast can you travel along that road, and how many vehicles can actually travel those things. So once you have all this information, you can build that gigantic, time-expanded evaluation graph. And this is what you see there for a tiny portion of it, obviously. This is essentially a residential area. And you can decide at every one of these points, how many people you want to evacuate, okay? So, you can wait, you can make them wait at that particular site, which we do a lot. You can also, there are some nodes that you cannot not use because they are flooded after that. And for the other nodes, you basically have the capacity. How many people you can, how many people can travel that lane and what speed, okay? And so, for instance, if you evacuate 20 people there, you can start deciding sending, some people along that edge, along other edges, make them wait. And so these guys are going to move across the network until they reach safety. That's what we want to do, okay? So the decision that you do in an evacuation like that is you have to decide when to evacuate, You have to decide where to evacuate, and then you have to decide how to evacuate. Okay, it's very different from a traffic simulation system. Okay, in traffic simulation systems, you have OD pairs. You know where people start, where they go, and when they do that. Even if people typically do stochastic analysis, sensitivity analysis on those. But here you have to decide when they leave and where they go and things like this. So there are many more decisions here. The objective is typically to evacuate, obviously, as many people as possible, and then, depending upon which state's emergency services and the kind of disaster, it's either delaying the evacuation as much as possible or making it as soon as possible. One of the big things that they have in Australia in the state emergency services that we are talking to is basically the speed constraints, where they say that everybody in one residential zone should actually follow the same route. And there are good reasons why you do that. It's much easier to predict what's going to happen to your transportation system. So you can build this massive multi-commodity flow over time, okay? So where basically the decision variables here are going to be deciding for a particular edge, the particular time, for a particular residential zone, how many people are going to be there, are going to be basically traveling that edge. And if you do that, you start from this very simple region there, and you get this massive network, okay? So this is about 4 million decision variables, discrete decision variables. And essentially, state-of-the-art mixed solvers essentially cannot even solve the root node. So we have to do something better. And so this is what we did. So what we did was starting by generating all these initial paths for every one of the residential area, and then we solved this master scaling problem. It's a very interesting problem. It's a very interesting formulation because we don't have to discretize all the edges. We only have to reason about how many people live at a particular time on a particular path. We don't have to reason about the edges. The path is sufficient. And then you have traditional constraints, like only one path is selected, and then the capacity constraints, and the link between the path and essentially the flow variables, how many people are traveling there. Okay? I don't have the time to go into details, but we have the paper as well, right? And so once you do that, you see how many people you can evacuate, and then afterwards you look at which nodes are essentially critical, you cannot evacuate them. So these guys here can only evacuate half of the population, and so there is competition on that link with that particular node. And so we take these two guys and we generate new paths from them, or more and more of them, right? And then we basically iterate this process. And so what I wanted to tell you here is that it looks like column generation, but in a sense it's very different, because every time we generate a path, it's like adding many columns, because every one of these columns, these paths have to be duplicated for every time. And also you add new constraints here. And finally, one of the things that we do is we solve the master problem optimally as a MIC, not as because we have a much better information about what are the critical nodes and what are the nodes for which we need to generate these paths. So I'm going to show you a demo of this. This is basically 35,000 vehicles being evacuated here. We are looking at the region from the north, so the flood is coming from the south. So the south is here, the flood is coming, you see the blue flood. Every one of these yellow things is essentially a road which is flooded, or a residential area becoming flood. And then you see this evacuation. And frankly, the first time I saw this visualization after looking at the data, right, so I was completely fascinated. There is no way a human can come up with that evacuation. It's highly non-sequential, doesn't follow the flow. It's basically a combination of how can you actually use in the best fashion the transportation network and evacuate the right people. So, I look at this almost every day. I'm so fascinated. So these are the results. So essentially the good news here is that you can essentially evacuate, you can evacuate essentially everyone, and you still have some time left. You can evacuate actually everyone, even if the population increased by 40%. If the population increased by 3-fold, we still can evacuate 87% of the people, but obviously we need mitigation measures for that. Okay, so if CDA grows too fast, we have to do something about this. One of the things that you can tell me is that this is an optimization model, so you have made simplification here on the transportation network and so on. How does it behave in practice? So what we did was basically running the results on a simulator, a traffic simulator, because now we have DOT spares when we have scheduled the evacuation. And we did that for various scenarios. We have people essentially, sorry about this, we have people essentially people don't necessarily do what you want. They leave a little bit early or a little bit late because they see other people leaving. Or they don't go they don't take the path that you want, they go to the closest evacuation center. And for many of these things, what you see over there is that the evacuation is really robust. We can evacuate everyone, so it's a good news. So the critical part here is to find the right time for evacuating a zone. If everybody does what they want, if they are really selfish and they leave at the time that you want, but they go do whatever they want, that you basically lose 20% of the people. You cannot evacuate 20% of the people. So we can really evacuate these things, and if you let people do what they want, you are not in a good position. So let me talk about relief distribution now. I won't go into many of the details here, but I will talk about some very interesting issues that I think are interesting from a policy standpoint. So this is the first project that we did in that space, and essentially this was about relief distribution, the strategic planning at the distribution level. And so, let's say that we have a commodity water, massive amount of water that we have to stockpile at different places. And we have to decide, the strategic level, where we stockpile the water and how much, okay? And once we have done that, when the hurricane is coming or the flood is coming, we have basically to find fast delivery plans. And this is massive amount of water, right? So one truck cannot carry everything. So it has to do multiple trips and so on. It's a complex routing problem. So obviously it's under uncertainty. The hurricane can do different things. And so some of the places where you actually stockpile may be damaged, they are not available or partly available. The demand may differ from one scenario to the other. So you have to optimize under that kind of uncertainty. And so essentially what you try to do as a strategic level is how much water you store at which places, and then designing essentially a very fast delivery plans afterwards when the disaster is hit. And essentially what DHS wants us to do is things like minimize the unsatisfied demand, try to give the relief to everyone, and then minimize the latest delivery time, which is very interesting. It's not a traditional routing objective, actually it's the opposite. And also minimize the storage cost. And typically we use robust optimization to do things like this. So I want to show you two interesting things, and these are real benchmarks that we use on the infrastructure of the United States, and also using national hurricane scenarios from the National Hurricane Center. Some of these benchmarks are actually pretty large. It's about 1 million decision variables again. And so what I want to show you, this is a crappy demo, but that's the purpose of the demo, right? So what you see there is essentially the routing, and it's an ugly routing, and it's good that it be ugly. Why? Because we are not trying to minimize the travel distance here. We are trying to make sure that we minimize the latest delivery times. And what this means is that you see the vehicles here, how much they travel. We try essentially to do that, we have to balance these vehicles. And so it's really good that this is ugly, because it's when this is ugly that we are actually optimizing the right function. Okay, so the second thing that I want to talk about is the way this is used for policy making. And so remember when I talked about the tsunami in Japan, one of the things that I told you is that the international relief effort actually hurt the relief. And so, there are pretty smart people at DHS and FEMA, and they knew about this. And one of the things they asked us to do is, can you evaluate using your system the impact of corporate donation? And so what you see there is essentially some of the plots we gave them. So on the x-axis, okay, so you have basically the budget that they have. And on the y-axis here is essentially the latest delivery time for the relief. And what you see here is two scenarios. One where basically where the corporate donor, let's say Walmart, is located centrally, and one where it's actually located at a distant location. And so what you see is that when it's located centrally, it helps to a certain extent if your budget is sufficiently large, and also when the budget is small, to actually get donation from let's say Walmart. But interestingly, if your budget is sufficient, okay, and you actually take this donation for the donor, it actually doesn't help at all, and it's actually hurting your efforts because we are not taking into account the additional processing that needs to be done at the DC level. So essentially, this was very interesting for them. They asked us this even before, obviously, the tsunami in Japan. And so what this is useful for is that if you use sophisticated optimization technology, you can answer some of these policy issues. Okay? So let me move to the third application here, which is the power system restoration. This is one of the ones that I'm the most fascinated about. Essentially, we are now looking at the restoration after, let's say, a hurricane, which is knocking down a part of your power network. And so, you have lines that are down, you have generators which are down, and so on. Some of the part of your power system getting islands and things like this. And so one of the things we do in that space is essentially trying to minimize the blackout. And what you have to do is schedule all these repair crews such that they will minimize the size of the blackout. So this is difficult because you have two complex problems that you are solving at the same time. One is the restoration, which basically means you have to find the right order as far as the power system is concerned for minimizing the blackout. And the other one is the logistic problem, just sending these crews all around. And so the two together are really a nightmare, and I will tell you why in a moment. I'm going to make some assumption here. I'm going to assume that we only reason about the steady state of the grid. We also have research on the transient stability, but I won't describe that today. So in a sense, what I'm describing here is basically the sequence of steady states for the grid that we have to reach. And I'm assuming that we can move from one to the next, and we have results to show that under reasonable assumption we can do that. So this is a picture of what we do. This is essentially the size of the blackout that you're trying to minimize. This is time, and this is the power flow. Obviously, you want the power at the top. Every one of these dots is a restoration action. You fix a line of generators or something like this. And obviously, when you fix enough of them, you have the power which is increasing. You can fix some other ones, the more of the power is there, and so on and so forth. And obviously, this is a bad restoration plan. Why? Because most of the power is restored at the end. Okay, we want to do better than that. And so there are these two aspects that I mentioned. One is the logistics. You have these vehicles picking up the part, taking them up the part, and then restoring, a part, let's say, a line. And this is what you see over there. And now the flow is increasing. The other vehicle is picking a part, restoring it, but the flow is not actually restored because the power system cannot do anything right now. It will wait until this part has been fixed, and then the full power is restored in the power system. So you have this logistic aspect, which are basically tied to the power restoration. Okay? Now, these problems are massive. You have basically pickup and delivery problems there for these things, which are, and several thousands of these requests. And obviously, you have to model the power system to evaluate the objective functions. And that basically means, modeling flow conservation, line capacities, constraints on grid and reactive power, and also the power equations. And these power equations are really nasty. One of the things they are is that they are basically non-convex, non-linear, okay? So in this picture, what you see there is real and reactive power. This is voltage magnitude. These guys are the phase angle of the voltages, okay? And so typically when people optimize over power system, they make some assumptions like these ones. They say reactive power is small compared to real power, so we remove this guy. Voltage magnitude has to be close to 1.0 in the per unit system, so you get rid of voltage magnitude. The conductance is small compared to the susceptance, so you get rid of that term. And then the sign of a small angle, typically we want a small, small angles differences. And so the sign of a small number is close to the number. And so what you get is essentially a linear system here, okay? And it's called the linearized DC model, okay? So we use that. But remember, at every one we do, let's say, a branching in a branching boundary or a move in a local search algorithm, we would have to solve that model for finding how much power we have to generate and what are the phase angles for these buses. Actually, the problem is even more complicated because these power systems are exhibiting Brace paradox, which basically means that sometimes you're going to add a line and the flow is going to decrease, which is like, that's a nightmare, right? So, so what you have to do is, in a sense, is decide exactly when you restore these lines, such that you don't decrease the power, because people would be really upset if something like that happens. So the system becomes non-linear again, but traditional techniques in nonlinear optimization allows you to actually linearize it. And you can tell me, but this Brace paradox never happens. For power restoration problems, it happens all the time. And so this is an example for one of the largest states in the US, and you see the Brace paradox over there. Now you can tell me, yeah, but MIP solvers are going to be good. So this is what good MIP solvers will do. After 4 hours, the duality gap is still about 8%. So at every node of this branching boundary or every local move, you have to spend 4 hours to get 8% duality gap. That's not very nice. Okay, so what we did was basically separating these two aspects. We solved power system applications for knowing what is a good restoration order for the power system, and then we use that for generating precedence constraints in the pickup and delivery. And so we solve these pickup and delivery routing problems with precedence constraints, which is very tough in itself. So we have to use sophisticated optimization technique to do that. So these are, once again, I'm going to show you some experimental results for the transmission system of the United States, and also, once again, hurricane scenarios for the National Hurricane Center. These are large systems, so 5,000 components in the transmission system, about 1,000 damage components. And I'm going to compare that with the practice in the field. This is some of the pictures that we have. This is the practice in the field. This is a combinatorial law of modes that we have. It's unrealistic. We assume infinitely many vehicles. This is what we can do. This is one of the results. This is another result. So basically, we were very happy. Sometimes we can decrease the size of the black hole by 50%. Okay? Now, one of the things you have to understand here is that we made a big simplification, right? So we used the linearized DC model, which is an approximation of the power system. So a very, very valid question here is that can you transform that solution into a real solution to the AC equation? And it's a good question because the system is under stress, and it's very well known in the power system community is that if you are not close to an operating condition, it's very difficult to find solution to this AC equation. Overbuy, this is a paper by Overbuy with one of the big guys in the power system. And we had the bad surprise because every solutions that we had could not be turned into an AC solution, or the DC solution could not be converted into an AC solution. So we needed help. And so what we did was basically spend 4 years learning about power system. It's a fascinating area. And one of the big things we try to do is to find good approximation of the AC power flow that can be used when the system is not stable. And we have to be able to reason about voltage magnitude, about reactive power, okay? And also we wanted this thing to be useful outside normal operating condition and to be embedded into discrete optimization solvers. And so we had to learn all the physics here. You see the real power, which is basically, this is all, essentially the physics affecting, the physics affecting the real power is basically controlled by the phase angle difference. Reactive power is controlled by the voltage magnitude and the phase angle. Both things are very important, and so we derive, linear and quadratic approximations for these things, basically using, convex or piecewise linear approximation of the cosine, and in the case of the linear approximation with, forced order Taylor extension, for the variation around the nominal values of the voltages. And the results were very interesting. So some of these traditional benchmarks in the power system community, so some of these have basically the linear HVC have some major errors, like 400 megawatt of errors. And we get something like 18, so it's much more precise. And when we apply that to the restoration this time, every one of the solutions we found could be actually turned into a solution to the HC equations. You may say, oh, did you lose something? This is essentially the solution of the DC model there. And you can see that we lose very little. And actually, with the convex quadratic relaxation that we have been working on with Hassan over there, so we can actually prove that some of these things, not all of them, but some of these things are actually feasible. So this is a demo of the kind of linear approximation models that we have. So this is essentially showing something where we are actually increasing the quality of the voltage and increasing the price of the reactive injection that we need to buy. And so blue is low voltage, red is high voltage. And you see essentially, when I move this thing, I want higher voltage quality or lower voltage quality. This is real time. Behind the scene, Gurobi is solving these problems. Okay? So it's a major development in that area. So let me conclude by talking about the perspective and the opportunities for ORMS. So one of the big project that we have is looking at a lot of the issues in this area. And the first thing we want to do is model all the infrastructure and everything inside Australia, map the entire Australian landscape. Most of these things I can't show you because they are confidential, but these are the kinds of things that we have on all the buildings in some of the cities. We know exactly who is in these buildings, what is the configuration, and all the 10 or 15 infrastructure that people are interested in disaster management. We are also building tools for sensing and monitoring, and also updating the state of the landscape and the GIS that we have. So one of the techniques that Nikta has developed is called hyperspectral image analysis, and the key idea is to use that for assessing risk in case of bushfires, for instance. So if you see these two buildings there, you may think, oops, these two buildings there, they are different colors, so human eyes can't tell if they are the same material, if they're the same risk fire. But when you use hyperspectral analysis, they are basically the same spectrum, and therefore they have the same risk from a fire standpoint. So this is essentially what you can do these days. So this is real-time hyperspectral analysis with the camera in a car, which is basically doing the analysis here, separating weeds and grass and bushes and things like this. Okay, so you can do that in real time at this point, and these things can actually be, you can buy a camera and the price is getting more and more affordable. We have also a team looking at understanding how people are actually working, are actually behaving in these disasters. So we have several people trying to use social networks and things like that to understand these things. I won't cover that. Another thing that we do is multi-agent optimization. In many of these disasters, we are basically at different agents that are restoring different parts of the system. The key issue is how do you incentivize them to do the right thing? And so this is a very difficult issue. And so we did some first step in this area by using essentially a mechanism design. So for instance, if you want to restore something in New York City where you have the power system which is down and also the telecommunication, and you have these dependencies between the power system and the telecommunication, we can design a nice mechanism which is all the nice properties, a small price of anarchy like 1.8 or something, and it's also incentive compatible, it's also individually rational and budget balanced. So this is the first step, a tiny step, but there are plenty of things that we can do in that direction, and I would love to work with people who are expert in that area. Finally, the last thing that we want to do is look at these disasters. Different disasters essentially have different behaviors. Some of them, like a hurricane, you can try to shoot at it, but it's going to not move, right? But while floods and fires, there are mitigation measures that you can do. And so how do you do that? Essentially, these are complex games in nature. And so some of my colleagues at Cornell and other places, and also we are trying to basically try to do these games against nature, but they are very, very complex. So let me conclude now. So this is one of the quotes that we got from some friends in Washington D.C. saying, since Katrina, the U.S. emergency services have improved drastically compared to Hurricane Katrina. Obviously, a lot of the credit is to DHS and FEMA, but a lot of people in RMS and other areas have contributed to that. So I think we can do much more, but the program, and we can work for many, many years on this, but I think this area, RMS is already having an impact in that area. And obviously this is the work of a large team, started at Los Alamos, studied at Brown University with some, really good undergraduates, and the various teams that make that, the flood team, the power system team, Hassan is over there, I believe, game theory, and obviously the data and network science. So thank you very much. I'll be happy to